So let me now proceed and to introduce today's speaker, Milan Allan. So it's very nice to have you here. And for those of you who don't know who Milan is, I will give you a brief introduction. So he got his PhD 2010 in St. Andrews while actually working in Cornell University, if I understood correctly. So with Felix Baumberger and Seamus Davis. And the title of his thesis was that the electronic structure of the nematic materials strontium ruthenate and ferropnictides. So basically on STM work on these quantum materials. Then he followed on a postdoc in Cornell. After that, he was an ETH fellow in ETH Zurich with Andreas Wohlraff from 2012 to 2014. And since 2015, he's at the Leiden University, first as an assistant professor, and nowadays he's an associate professor. And he also got one of these ERC grants in 2017. His group is working to explore and understand new quantum states of electronic matter at the atomic scale, and they are of course using the scanning tunneling microscopy to visualize the relevant quantum mechanical degrees of freedom. And they are also heavily involved in building the instruments and developing different kinds of methodologies and techniques to basically address interesting questions. And there's quite a long list of different kinds of systems that Milan's group has looked at over the recent years. So they've done scanning tunneling noise spectroscopy, they've looked at mode physics and high temperature superconductivity, Georgeson, STM, strange metals, magnetic fluctuations, electron spin resonance, and also some work on twisted graphene bilayers. And today, the title of his talk is Cooper pairing without superconductivity. So I think with that, we very much look forward to your talk. So the floor is yours. Please.
Thank you very much. Good. Thank you very much, Jose and Peter, for organizing this wonderful colloquium series. I've enjoyed a lot of talks before, both in person and on YouTube afterwards. So I'm very happy that this series exists, and I'm very happy to be here today. I'll talk about Cooper pairs without superconductivity, and then later, if time permitting, a little bit about heterogeneous superfluids in iron-based superconductors. But please don't hesitate to interrupt me. Please don't hesitate to ask questions and comment. You know, if there's not enough time, I'll manage very well. So I'm happy. The more interactive it is, the happier I am. The work I will present today is done with my colleagues, Koen, Dewey, Damianos, Willem, and Jackie from my group. And let me put this to a laser pointer. Well, I should also mention that Koen just won the Afanadjeva Ehrenfest Prize for the best doctoral thesis in physics in the Netherlands. So I'm very happy about that. And Dewey has left the group and is now an assistant professor at Yonsei University at Seoul. It was also a pleasure to collaborate with our colleagues Jan, David, Edward, Teun, Mark, Peter, and Genda, who all brought their expertise into this project, including sample fabrication, which is something that we don't do. Now, as Peter already very nicely introduced, our group is an STM group or scanning probe group. That's why I give a talk here, I guess. But our overarching goal is to understand quantum matter in these materials where ensemble of electrons form exotic quantum states that often lead to peculiar macroscopic properties without a microscopic understanding. So these are some of the systems we study. One thing we really try to push in my group is that we have the connection between instrumental design and physics. So we want to always be able to investigate the questions we deem most important with new instruments. Like many of you, we build our own heads, our own STM heads. We have this platform of smart tips where we're happy to collaborate if somebody's interested. The goal is to allow for nanofabrication, microfabrication to be integrated very close on the tip. So this is something we've developed, and if somebody would like to collaborate on that, we'd be very happy to do so. I'll talk about high frequency impedance matching today, And in the end, I'll also talk a little bit about Josephson STM, which again is something that many of you have really pushed forward in the last decade. Now, I'd like to start this talk by taking a step back. You all know that there are two kinds of elementary particles, right? There are fermions who, have to obey the Pauli principle and cannot occupy the same states, and there are bosons who kind of like to occupy the same state. And one thing that I really like about solid state physics is that it allows, in principle, for a much richer physics, for much more. And that holds even for, seemingly mundane and well understood material like aluminium. My favorite example is Cooper pairing and superconductivity, which we know how it works due to the Bardeen-Kruper-Schrieffer theory of superconductivity, or brief BCS theory of superconductivity. What happens is that we start with a sea of weakly interacting electrons, or perhaps more precisely, Landau quasiparticles, but we usually call them electrons just for simplicity. And then we know that, thanks to Leon Cooper, that at low temperature, if there's an attractive interaction, any attractive interaction between two electrons, and there almost always is, this state is unstable to the formation of Cooper pairs. I drew one here with orange. Even in the simplest case, this looks a little more complicated. This is the relative probability function. It's kind of a wavy function that gives you the shape of a Cooper pair, if you will. So the state is unstable to the formation of Cooper pairs. And the cool thing here is that Cooper pairs are not fermions anymore. They're actually much more like bosons. They're almost bosons in the sense that in certain limits, their commutation operators, commutation relations look like bosonic commutation relations. And you can imagine that if you want that, you add two spin 1/2 particles and you get, which are fermions, and you get one spin 0 or spin 1 in certain cases, almost boson. Now, because they're almost bosons, because they behave like bosons, these Cooper pairs can then condense into the macroscopic quantum state that is the BCS ground state, and that is the superfluid. I try to indicate here that these Cooper pairs usually are very large compared to the density. That makes them overlap a lot, and that is the reason why the state is often so phase coherent, while phase coherence is so rigid. Here's also the equation of it. So you can see that the P here always adds 2 electrons. It's the U's and the V's that add all the magic. So that's where the coherence, for example, is encoded. Now, in conventional superconductors, pairing and condensation always happen concurrently. Above TC is the transition temperature for superconductivity, you have free electrons, and then at TC they pair and immediately condense. So that's usually how we talk about Cooper pairs, right? We talk about them just in the context of being the constituents of BCS superconductors. However, there's a possibility that you can have Cooper pairs in a metallic state that is not superconducting. So this is in principle, from theory, is allowed. And this fascinating thought is what we want to investigate in this project. So this is the core of my talk, to explore Cooper pairing, in our case above TC, in a superconductor called titanium nitride. I'll talk a little bit more about titanium nitride specifically, but before that, let me spend a bit of time to talk about what the theoretical possibilities are that you can have Cooper pairing without superconductivity, in this case above TC. And I think a particularly intuitive way to look at that, one way that I very much like, is in the Bcs Bec crossover. So Bcs here stands again for Bardeen-Kruper-Schrieffer, Bec for Bose-Einstein condensation. And these are the two limits. This one I already told you about. The other limit is that you have very tightly bound pairs. So that's called the molecular pairs that exist both above and below TC. And what changes is that below TC, they're phase coherent, they're superfluid. Above TC, they're not phase coherent, and you have a metallic state that is made out of bosons. Now, the nice thing about this crossover is that you can have, you know, a continuous crossover between these two extremes. On this side, you have pairs above and below TC, and TC is limited by the coherence temperature. On this side, TC is limited by the pairing temperature. And theoretically, I think we understand quite well what is happening here. We understand quite well what is happening here. In between, it's a little less known. I should also mention that both experimentally and then as a follow-up theoretically, we have to thank the field of cold atom physics for knowledge about the Bcs Bec crossover. So all these states here have been actually realized in the cold atom physics. While in solids, I think we know quite well that this scenario does not happen. We know that this scenario does happen actually in basically almost all conventional superconductors, and we don't really know how much of this stuff here is realized in solids. Good, so that's the Bcs Bec crossover. There's another possibility about having Cooper pairs above TC that I want to mention, and that's fluctuations, superconducting fluctuations. So in any phase transition that you can imagine, right, you can have fluctuations around the phase transition. Because of the rigidity of Cooper pairs in BCS, this is usually a very small region. Delta T over T can be, I don't know, 10 to the minus 14, 10 to the minus 16. So this is a tiny region where you have fluctuating short-lived Cooper pairs. However, in special cases, usually it's two-dimensional disordered cases, and the sample I'll talk about today is such a case. You can have a much broader region, up to, I don't know, 2 TC, you know, is quite common. And in this region, you have fluctuation. So these are not, it's a very different case than this here, where you have all these preformed pairs. It's fluctuation of finite lifetime Cooper pairs that influence the properties of the materials in rather subtle ways, for example, by increasing the conductance. And they have been explained theoretically by Aslamazov, Larkin, close to the boundary, and Markey Thompson at higher temperatures. Good. Any questions so far?
May I ask
please interrupt.
So in yes. The pillar where you show incoherent pairs, so you have the pairing temperature T pair, but that's not a superconductor, right? So what happens there at TC? What's the difference between the upper half and the lower half in that column?
They become phase coherent. So below T, you mean between here and here, right?
Yeah.
So here you have a phase coherent superfluid. So here you have all this beauty of a superfluid, right? You have a macroscopic wave function, you have a macrocosmic current, you have superfluidity, and so forth. So this is basically the Bode-Einstein condensed version of this. So right. I think the way to look at this is
refers to the upper half. Now it was a bit confused. It says incoherent pairs, but that refers to the colored part.
Oh yes, sorry, yeah. You're right. This is not the most clear labeling.
No, it's okay. Yeah. Thank you.
Yeah. So this is for people like you who are used to superconductivity, this is kind of the intuitive way, but for other people who think about Bose-Einstein condensation, this is kind of the standard way, right? These are bosons and then they Bose-Einstein condensate.
Milan, can I ask one quick question? So
sure.
Are you separating these two things, the pairing itself and the phase coherence process? Or basically these are the same thing, that the pairing mechanism and the phase coherence is just like you have randomization process which prevent Cooper pair from forming condensate. So is that what we are looking at?
So here we have the same thing, right? Pairing and condensation happen at the same thing. So with condensation, I mean that you get this phase coherence and that you have a superfluid. Now, what I want to start thinking about is that while we're used to this case because we deal with aluminum and lead and these materials, while we're used to this case, there's actually a rich landscape in theory where you can have these two things separated, which is experimentally quite nicely explored in cold atom physics, but as I said, in condensed matter physics, not at all, or well, okay, I shouldn't say that. In condensed matter physics, it's much more challenging to explore that. Yes, I take that back. It's been explored a lot. It's just very challenging. Good. So now, yes.
Sorry for interrupting. There's one more question in the chat, which is if we can observe superconductivity in the not paired region. So whether if Cooper pairs are necessary for superconductivity.
Yes. Now, they're not necessary for zero resistivity. There are cases where you can have zero resistivity in materials without superconductivity, like in very different, you know, corners of physics. Usually usually you need some topology, right? In some quantum Hall states, you could have zero resistivity. But superconductivity, this phenomenon, you need pairs.
Yep, thanks.
Good. So where can we find Cooper pairs without superconductivity? And very generally speaking, I think the systems, in my opinion, the system where you have the highest chance to find them is in what we can call fragile superconductors, or in some cases, for some materials, people call them marginal superconductors. Superconductors where phase coherence is, for one reason or another, very fragile, and therefore they're susceptible to have this phase coherence destroyed. So this happens in high temperature superconductors, where it's mainly the fact that these Cooper pairs are small and that the density of electrons is small that makes them fragile. They happen in interface superconductors like LAO STO, for example, where you again have low density of Cooper pairs. And probably the same holds for twisted bilayer graphene. You can also have fragile superconductivity in disordered systems. This is what I'll talk about today. There, the disorder makes the phase coherence so much more fragile. And this has been explored both theoretically and experimentally. Now, let me give an example of experimental exploration. This is from a photo emission. And it's a high temperature superconductor. It's for those of you who are familiar with these materials, it's the one that people usually call a cuprate Bisco 2201. And you can see here TC is indicated with these white circles, and this here is T pairing. So they say in this paper, they explored that some electrons might be paired below this line. And how they extracted this is by looking at the coherence peak, and you can see at some point they get weaker. This is TC. Then at some point it fills even more, and they just made some threshold at which it's more filled, and this is T pairing. And this shows, well, it first shows how beautiful photo emission as an experiment is, but it also shows the challenge with to extract information about Cooper pairing. You usually need some model, you need something to compare to. That holds for transport, which, you know, where there's also a lot of information about pairing, STM, where there are several papers that explore that. But in general, it's just very hard to explore pairing with these probes. Especially, it's hard to say more than just, you know, there's some fluctuating Cooper pairs, to distinguish between these cases, to give some quantitative measure. Now, why is it challenging? Well, first, because the charge of one Cooper pair is the same as the charge of two electrons. So that's why, for example, in transport, you need to look at sometimes subtle, sometimes less subtle effects of how a Cooper pair is different in transporting charge than two electrons. The other challenge is something that I'm sure this audience very much appreciates, and that's, you know, the heterogeneity and trending in these materials, right? You all do STM because you can measure stuff that you cannot measure with sample averaging probes, and especially in quantum materials that tend to be so heterogeneous, it's challenging. So what we wanted to do,
before you go on, there's a question from the chat from Dario.
Mm-hmm.
So how can we characterize fragile superconductivity?
You know, there's no strict definition. I was thinking about yesterday how I should call them, and I call them fragile. There's marginal is a word I very much like, but I think the people who invented the word were thinking mainly about disordered superconductors. What I mean here is really just, you need to find some reason why phase coherence should not be so, you know, as strong as it is in materials like aluminium. And then one very naive way of thinking is, as I said, you think, well, phase coherence is strong because they overlap. That's why mean field works so beautiful in superconductors. Then you think, well, let's make them smaller and let's make the density smaller. That's what happens in high TC superconductors, right? They're doped insulators, so the electron density is very small. Good. So what do we want to do? How do we want to investigate it? Well, we want to combine scanning, tunneling, microscopy to get local information, and very importantly, to get a beautiful, clean vacuum barrier for tunneling, and shot noise spectroscopy, which I think is a really beautiful, unambiguous probe of pairing. Now, let me tell you a little more about shot noise spectroscopy, because, well, STM, I'm sure you all know very well. So shot noise spectroscopy, what we do here is we measure not the time average signal of some value, in our case, the tunneling current, but we measure the fluctuation or the noise of this signal. And this gives a lot of information. In general, we can calculate what the noise of a tunneling current should be. The noise S is equal to 2 times the charge of each charge quantum that we tunnel times the absolute value of the current. This is just Poissonian statistics, so nothing special here. It's simply a consequence of the fact that charge is quantized because, you know, electrons exist. These curves, then if you plot, you know, noise against current, you get curves like this. This little rounding here is due to temperature, and then you have the linear rays on both sides. Now, what happens if you have pairs, or what happens if you transport the charge, you know, in a bunched way where you always have 2 at a time? Well, then your effective charge is 2, and you get double the noise. And so this is a very nice probe to see this difference. It has been explored since a long time in mesoscopic physics, and I cannot, you know, introduce all of them. So I'll do like I'll show you 2 very nice works. One of them is with niobium and niobium nitride, and I think this very nicely shows you both the beauty and the potential of the probe, but also some of the challenges. Let's take a look at this. Let's take a look at this curve first. Let's ignore the things here at low energies. So this is a function of bias. Just look at this step here. So you nicely see once you enter the gap, the superconducting gap, your effective charge goes from 1 to 2. And that's niobium nitride. So this very nicely shows that electrons are paired. You also see the other curve here, the black circles. This is niobium. And of course, niobium is also superconducting. But the fact that you don't see the step has to do with the interface. So it's very hard to make these interfaces. It's very hard to interpret these interfaces in mesoscopic physics. In the cuprates, it's even harder to make tunneling junctions because of chemistry. And only very recently has it become possible to make a tunneling junction with cuprates. And in this very nice work, they then explored the shot noise, and they saw, well, it was quite spectacular and quite mysterious in the sense that the noise is enhanced almost everywhere, even outside the gap. It's not quite clear to me. Well, it's mysterious in the sense it's not clear to me what really causes this enhancement. So let's go back to STM.
Milan,
so let's try to make this local.
Yes. Interrupting, but there's.
I'm happy to be interrupted.
Yeah. So there's a question which is if one can see Meissner effect or some remnants of it.
You shouldn't. Now, I'm not sure if there are any cases where you can see a remnant or so, but in general, not. I assume that's meant in this paired material. You can sometimes see, you know, depending on which theory you believe causes the breakdown of superconductivity, you can see some effects of, for example, vortices, right? You might be familiar with Berzinski, Koselleck's Dulles transition, which, if not, I find it a beautiful, intuitive way of looking at the thing, even though the theory is for neutral superfluids and definitely does not hold in our sample. This physics of vortex-anti-vortex pairs that unbind, I find very nice. And then there are probes that access the fact that there are vortices above TC. But Meissner effect, no, I don't think that's a good probe. Good, so we want to bring shot noise to STM. Now, you all know STM, right? So you know that in conventional STM, it's very hard to have a high bandwidth. It's very challenging to do high frequency. Just because, you know, you have your giga-ohm resistor, and we didn't want to make an instrument that only works for kilo-ohm in the point contact regime. We really wanted to have an instrument that works with a giga-ohm resistance. And that plus the capacitance just gives you a low-pass filter, and then you can measure your signal really in a range that is not fun to measure, because you have 1/f noise. If you go a little bit higher, you also have mechanical noise. So that's not a good way to measure shot noise. What we did was we tried to bring this measurement range to higher frequency, because shot noise is wide, so you can measure it at any frequency. So we brought it to, in our case, megahertz regime, while keeping this here for the feedback and all, you know, spectroscopy and all this stuff. Now, how did we do that? There are different ideas, have been explored also by other people. I want to especially highlight Berg. They did some follow-up, some bootstrapping of a HEMT, which was very nice. Also in Paris, there is a work that uses a very similar design to us. What we do is we have two tag circuits, one for the DC signal and one to bring the bandwidth. Well, together they bring the bandwidth for high frequency to the megahertz regime. We use spot welded superconducting inductors here. We use a special low noise HEMT, and then we try to make this circuit as close as possible to the STM head. You can see here, that's our design. This is actually the first generation that I'll talk about today, which is built right next to the Unisoku STM head. And yeah, so you want to have it as close as possible. If you're interested in this, you know, we have a technical paper. We're also very happy to help if you have questions and so forth. If you want something faster, Unisoku just started to sell basically exactly the same circuit. We worked with them together, so they you can buy a shot noise circuit like this also now commercially. Now, a typical noise curve looks like this. These are somewhat different conditions. So it's around 3 megahertz. It's as narrow as it's quite narrow, so it's not a broadband measurement, which in our case is good, right? Because the two things we want is as low capacitance as possible. But then once we have that, we want as high Q as possible. So if you want to have a broader bandwidth, by just reducing the Q, in total you lose signal. So we're happy that this is actually very narrow in bandwidth. Then you can use that for several things that are not shot noise. You can use it, for example, to make your spectra in the DIDV cleaner because you have less noise. We haven't really implemented that from a software point of view, so we just tried it once in a week by artificially coding the DIDV. This here is our common, I think, 57 hertz measurement, while this here is on the megahertz. You can see it's a little bit lower noise, but again, we haven't explored that. You can also use this technique to look at other sources of noise. This is a measurement that shows enhanced superpersonian noise in a cuprate high temperature superconductor, and we can interpret this as a proof that there's really polaronic physics going on in the charge transfer layer. This is not something I'll talk about today, but I want to mention it. If you want, you can ask questions. Otherwise, it's published. You can also look at the paper. Good, but let's go back to shot noise. Let's go to our first test on gold. This here is the shot noise curve as a function, the shot noise as a function of current, and you can very nicely see how it goes up linearly around, you know, in the positive and negative direction. We can then divide this by the current to get the effective charge, and not surprisingly, the effective charge of electrons tunneling from a gold sample is 1 electron charge. So we were very happy with this test, and we wanted to go to materials that are a little more intriguing. So we went to a SIS junction with a lead tip and a lead sample. Now you can see outside the superconducting gap, the effective charge is still 1. And you might have noticed that I switched the x-axis from current to voltage. This is easy because we measure at constant junction resistance. So this way we can see, you know, we can do it in a spectroscopic manner. So outside the gap, it's still 1, but then inside the gap, it beautifully doubles. So it goes from effective charge 1 here to effective charge 2, because now we're inside the superconducting gap. So we were very happy. This allows us to use STM as a probe for pairing. And so far, we're still, I think, the only group in the world who can measure pairing in this way with STM, although I'm sure that will change soon. I hope this will change soon. We can do it in a mapping way. So we can do this spatially with spatial resolution. Our sensitivity is not where we want it to be, so we're still struggling with this, and we hope that in the future we'll build better circuits. But here is the noise, again, not very surprisingly, which is very homogeneous, one in a gold sample.
Milan, can I have a quick question?
Yeah.
Have you, well, this is extremely interesting. Have you ever looked at the interface with normal material, like a superconducting normal? And you see, yes, for example, how it changed the number. I mean, sorry, the pairing, basically.
Yeah. Interface. So actually, the rest of the talk will all be about NIS junctions.
Okay.
And it's a good question, because I haven't actually told you why the noise doubled, right? Because they're not pairs tunneling. We're not doing Josephson STM here.
Yeah.
The reason why we have pairing is because to insert or extract a charge inside the superconducting gap, you need an Andreev process. And the Andreev process will lead to bouncing, and that will lead to a doubling of your noise here at 2E in the SIS junction. At lower energy, you even need several of these Andreev processes. If you remember this mesoscopic data I showed you, you could see how it go up. In the NIS junction, which is what you asked about, it's actually simple. You just get a doubling at delta, and then it stays like this.
Okay.
Milan, sorry, before you go on, there's a question from Frank Massey. So he's asking that how do you take into account the fact that the dynamical junction resistance, which changes dramatically in the superconductor, affects the impedance at resonance of your tank circuit?
Fitting. So the noise curves I showed you before, right? You could see that they all have different heights. That wasn't because, so I said then I think they were taken on different conditions, and this wasn't because there was so much or less, more or less noise. It was because the Q changed. So the impedance changes, and that changes the Q, but you can extract that by fitting. So the nice thing is that this basically gives you a DIDV spectrum at the same time as you measure a noise curve. It's the most inefficient way of measuring a DIDV spectrum, but it gives you some confidence if the DIDV spectrum that you get by extracting the Q is the same as the one that you measure conventionally. I hope that answers the question. Good. So next, we wanted to measure disordered superconductors, disordered superconductors that are close to a superconductor insulating transition. Now, I'm not sure how familiar you are with disordered superconductors, so I'll give you a very brief introduction, but feel free to ask more questions if that doesn't make sense. So these materials are very disordered, hence the name. They're 2D films with very mean-free path, very small mean-free paths, like, often going to numbers where it doesn't even make sense, the concept of mean-free path. You generally determine the disorder by just changing the thickness of the film. The thinner they are, the more disordered they are. And of course, they're materials where there was a lot of talk, there's lots of signatures about superconducting fluctuations above TC. I think we know that there are superconducting fluctuations from TC from many, many probes. So that's why we chose the materials, also because they're technically quite well suited for our instrument. Our sample that we measure is titanium nitride. It's 45 nanometer in thickness, and it has a TC of about 3 Kelvin. Now, one thing that was important to us, because these samples are always very challenging both to measure and to characterize, we measured data from both atomic layer deposition samples and ones that are sputtered, so very different fabrication techniques. And indeed, they showed differences in our SCM measurements, but the key element was the same. Here's a topography, and here are spectra. These are spectra from the two different samples. Now, these are the topographies on disordered superconductors look something like this, right? They're usually either amorphous or microcrystalline. So, it's not pretty, I would say, but on the good side is that you can usually get them cleaned quite easily and you can get stable junctions. A lot of STM work has been done on disordered superconductors. Here I named just some of the names: Chapelier, Sassepé, Raichaudhuri, Balamkov, Brun, Rodichev, Vinokur. So there are many great STM works on these disordered superconductors before we even started these experiments. But let's go to the noise. So this is a noise curve. This is in the superconducting state. Nicely, you see that outside the gap, you have charge 1. And then when you go inside the gap, this is now at much lower energy. So that's why there's much more rounding. At lower energy, you get a change from noise charge 1e to charge 2e. But you can also see nicely. So our instrument works, which perhaps, at least to me, was a little more surprising than it might be now in the talk, because the gap looked a little weird, right? I'll come back to that later. So, but clearly we have pairing below TC in these disordered superconductors. Now let's go to the key measurement of this project, the temperature dependence. I start with 2.3 Kelvin, which is just the lowest temperature we managed to get at this time. So this is a little bit below TC. I also now have these orange dots. This is from the sputtered sample versus the ALD sample.
I'm sorry,
yes.
So why does the shot noise not jump at delta, but instead it smoothly evolves?
This is temperature. So our temperature is a little, it's rather high compared to TC. And then, well, in the case of lead, you can explain this quite nicely, right? Because you have Andreev processes that go with the probability of T squared, where T is the transparency, and quasi-particle processes that go with T. So what it means is that once you hit delta, you still have some thermally allowed processes with quasi-particle, and they will dominate, and they will give you noise 1e, and then more and more you have the 2e noise. So that makes your process, quite smeared out. Basically, it's the Fermi function of your tip.
Okay, thank you very much.
Good, so let's go a little bit above TC, at about 1.3 TC. Now, clearly they're still pairing, right? Clearly this line still goes from 1 to 2, which is the first, key result of our study. The pairing persists above TC. And it's not just a little, some of the electrons. Really, it looks like almost all of the electrons are paired. Now, at 2 TC is still the same, and only if you go quite high in temperature, around 7 Kelvin, it looks like this line goes back to 1e, although I have to say that our error bars also explode at these temperatures. Good. Now, how can we explain this? Or how can we learn more about what's happening here? Let's take a look at the spectra. Now, this is the superconducting gap I showed you before. As I said, in the other sample, there's a little bit of a coherence peak. Here, not really. Now, if you look at the numbers, this is not something that I would call a nice superconducting gap, right? It barely is a gap. And when you raise temperature, it actually completely fills even at TC. So this gap is rapidly filling up, which is something that we know from quantum materials. Heavy fermion materials, for example, this is data by Yastani group. This is data by Seamus Davis group that I and actually Freek, who asked the question before, were involved. Same in the cuprates. You can see a lot of these gaps don't go to 0. Often this is attributed to either artifacts or to phase fluctuations above TCs. So the same holds here. So let's look at this quantitatively. Here's the gap. As a calibration, here is the temperature curve with a TC of about 3. And then let's look at how this gap filling works. So we have here, we just looked at the numbers inside the gap. We compared it with the number out at that kind of flat curve. You can see it rapidly fills, and then it's basically filled at 4 Kelvin already. This is, you know, if you look at the thing here, I think by human eye, you can really see that this is filled. Now you can also look at the gap width. And this you should see as kind of more a phenomenological number, right? A gap like this, I'm sure you all know you cannot very precisely fit it. So we extracted it with second derivative. We also fit it and we got kind of the same result. And what is very robust is that this gap doesn't close. So it's not like a BCS gap that closes a TC, but it's more something that fills up. And if you would calculate the BCS critical temperature that corresponds to this gap, it would be far above TC, around 11. While if you would calculate the gap that you expect with our TC, it would be much smaller. So this hints also towards something where pairing temperature is much higher than the superconducting critical temperature. Now, next, I want to compare this with how many electrons are paired. So here, this is the effective charge outside the gap, 1 effective charge inside the gap. And again, this is something that I hinted before. To me, the most surprising thing of our result is that this is not a partial, you know, pairing. It looks like almost all electrons are paired here, despite the fact that the gap looks like a metal. You know, there's no, like, spectroscopically, we have a material that looks like a metal, but instead of made out of fermionic electrons, our experiment hints that this metal is made out of paired electrons. I also want to compare this with transport. So in transport, you can see if you zoom in, you know, right at this value above TC, you can see that the conductance slowly goes up. So it's a broad transition. This has been interpreted in the framework of Mackie-Thompson in fluctuations. But other than what I would expect from the Mackie-Thompson framework, again, here it's not some short-lived Cooper pairs, some small population of short-lived Cooper pairs, but actually pretty much all electrons that are paired. So taken together, what we see is a gas or liquid of Cooper pairs that is far above TC without a spectral gap in a material that otherwise looks like a metal from an STM point of view. And I hope that, you know, this is just a start. I hope that there's much more we can do with noise. We would like to investigate D-wave superconductors. We're working on that, but I think to really seriously and nicely do this, we need orders of magnitude higher sensitivity, because the nodal quasi-particle really makes things much more challenging here. We would also like to investigate more the whole phase diagram of disordered superconductors. We would like to go close to the superconducting insulating transition. Then another thing that I'm very excited about is all these artificially made structures with weird quantum properties that many of you are experts. This is not something that we know how to do in our group, but it's something that I hope that shot noise can sometimes be helpful to differentiate between, let's say, YSR state or Majorana states. Good. And with this, I would like to conclude. Well, I wanted to say conclude this part because I had some short thing about something else, but I think I'll skip this and go to the end because now it's already time. I wanted to tell you a little bit more about the heterogeneous superfluid, which we measured in another one of these materials that, you know, that are fragile in the sense that they have very small phase coherence. What we measured there is that the amplitude is actually very heterogeneous as well.
Yeah, I think, Milan, I mean, we already had some questions. So if you want to take five, max 10 minutes more, it's no problem. So.
Okay, let me show you some pictures. If I manage to do this here. Good. So here what we wanted to investigate is, you know, another difference between conventional superconductors and these fragile superconductors is that you have in principle the possibility for inhomogeneous or heterogeneous order parameter. This is something that has been proposed You can have, pair density waves, FFLO states, which is something that I think you're familiar with. There's good evidence that this exists from transport, neutron scattering. It has been visualized by STM recently, and from cold atom physics, we also know that these states exist. Another possibility is non-periodic inhomogeneous superfluid states. And this is what we wanted to investigate. What we used here is Josephson STM, which is something that many of you have really pushed forward. I want to note one thing here, I think that might be nice for people to see, because it helped us. When we started this project, people would tell us that if you want to do Josephson STM, you really need to have an insanely expensive millikelvin STM and spend years on filtering. And okay, we did spend a year on filtering, but when you look at the equation of Josephson STM, if you want a stable, nice, phase difference between tip and sample, then you need very expensive equipment, and it's very hard. But if you want to investigate the superfluid density by looking at the Josephson peak, and that's basically what almost all STM groups so far, with a few exceptions, are doing, you can do that at 3 Kelvin or 2 Kelvin and get interesting measurements. So for example, our data from lead is shown here. You can see here nicely the Josephson peak and some of these wiggles outside that I think Christian Ast and his group first explained as the mode of the tip. So you can nicely do experiments, and I think really explore interesting physics in quantum matter without a dilution refrigerator STM. That is not to say that it's not nice to have one. We're actually building one right now, but still. Good. So what we wanted to do is not measure this on lead, but to bring this to a quantum material, which is hard because of the fragility of these tips. So I think we were the first one to manage to do that. We chose a material to investigate that has this fragility of superconductivity, and then we wanted some other things that make it technically easy, like a flat gap. So we chose iron selenium, telluride selenium, which is an interesting material in its own mind. We got data, we got nice ways to explore this, and I'm going very quick and not even explain it, but I'm pretty sure many of you know about Josephson STM, so how it still works. And as a result, well, let's go just to the chase. We found that the superfluid is indeed very heterogeneous in these materials. It's not periodic, but it's very heterogeneous. And we were wondering, well, we wanted to find a little bit why this is the case. So we looked at the usual suspect: chemical or structural disorder or scattering. Strong scattering between electron can lead to pair breaking, and that might be what leads to the heterogeneity. Now, this chemical structural disorder was not the cause. We know that by just comparing with the topography, calculating correlation function. The scattering we can explore by looking at QPI. This is on the rhodates where it looks beautiful, but we could do the same on the iron selenium tellurium surface where it looks a little less beautiful. Look at areas where there's strong scattering and there's no correlation. So we could rule out the usual suspect and find something else that very nicely correlates, and that's a quasi-particle strength, how sharp the coherence peaks are. And that really correlated well. It's about 0.6. And this really suggests that superconductivity is needed to have coherent quasi-particles locally on the length scales of Cooper pairing. It's a theme that has been explored in general in the Cooper rates, for example, with photo emission as a function of doping, and we could see it here locally in a microscopic fashion. So this was the short version of the heterogeneous superfluid in iron selenium beryllium. And yes, here's the conclusion slide with also the noise as a probe of pouring and the Cooper pairing far above TC. And with this, I want to thank you for your attention.
Yeah, thanks a lot, Milan, for this really inspiring talk on how to measure these Cooper pairs in the absence of coherence. So now we have some time for questions. So if you have any question, you can either write it in the chat or raise your hand and we will let Milan know about it. So there's already one question. Sander, please go ahead.
Yeah, Milan, a wonderful talk, and I really enjoyed this. It's beautiful results. I have a very naive question, so apologies for that. And actually, it's a little bit related to my earlier question. So all the way at the beginning of your talk, I asked what happens at the transition that we actually currently also see on the right, where you have a material where your pairing temperature is above your superconducting transition temperature. So above TC, you have pairs, but that are let's say, correlated or non-coherent, and below you have coherence. My question is that transition still a sharp transition? So you already have pairs. So why would there be a very sharp temperature that all of a sudden they become coherent? Why can that not be a gradual thing?
So it is a phase transition. Now what happens here is that in Illustrator, I change the color of the pairs. What happens in the physical models, you know, it depends a little bit on models, but I think very nicely, for me, the intuition in my back is always the case which is not really valid here, but the case for neutral superfluids, the BKT transition. And there you have these thermally excited vortex-anti-vortex pairs, right, that start to pop up. And they don't destroy completely phase coherence, but at some point they start to unbind. And this is a phase transition, the unbinding, when they start to unbind, and that will then destroy your phase coherence. But it is a transition. You can see that in specific heat and so forth. It's sometimes a bit weird, but you know, it's not always completely clear, but it is a transition. It's an interesting transition because, you know, in the couplates, for example, with STM below and above this transition, even though it's so spectacular in transport, right? Superconducting versus non-superconducting. With STM and the ARPES, if I would let anybody guess where the transition is, you couldn't guess it, right? Which is always something that fascinated me.
Okay, so you don't see anything happen in your data at that TC, but from other experiments you infer that there is a sharp transition.
Other experiments being transport,
right?
In our case, but I admit that now. I wouldn't put my hand in the fire that I remember how exactly the other probes look like, but you can often see that it's really a thermodynamic transition from other experiments, including specific heat.
Right. Thanks. Cool.
There's another question by Dario. Dario, please go ahead.
I'm not the next one. I think there is a debut before me.
Oh yeah, sorry. Abdu, please go ahead.
Okay, so one of the things that's really nice about short noise that you presented, the symmetry of Cooper pair. And I think this would be really remarkable. For example, you mentioned the challenge of nodal, particles and all of that. So if you take a D-wave superconductor, so my question is like, how sensitive the short noise to spatial, variation? So I guess you have the same resolution, right? Or you would expect that the spatial variation is the resolution in a spatial variation is very small. It is the same, right? So if you do a spectroscopy, right, along the D-wave superconductor, high TC, you are already in the superconducting states. And we know that Cooper pair find it easy to move along certain directions. Those are the antinodal. Can you decipher nodal direction from antinodal direction in TC, in high TC, using the short noise technique? That's my question.
My naive guess is no. It's hard to use this probe to find direct evidence for the symmetry. For that, you'll need some phase microscope to see the phase.
I know, but still, you are able to see areas where Cooper pair are not to be found, for example.
Yes.
Right? And if we take a spectroscopy along certain direction, and perhaps, well, at least we find those directions, not necessarily, we prove that there is some nodal direction along this lattice, and that would infer some symmetry other than S, at least, right?
Yes.
So we can do that.
Yes.
Okay.
Now, to be honest, I don't think there's any doubt that high temperature superconductors are D-wave.
No. I don't doubt it, but I think
there's a lot of other things that I think. So I'm very excited to measure them with shot noise, less for what you said, for the order parameter symmetry. But just because there's so many things we don't know, right? For example, we know that this is the gap, right? But we also know that in underdoped, you have about 10 different explanations to what this gap is. One of them is people say this gap has to do with pairing, but it could be charge density, it could be some weird order. It can, there's so many explanations. So if you could show that this gap is due to pairing, it will already be incredibly important. And if it's not, if you could show where the pairing gap starts, that would also be incredibly important. Now, we of course tried this, but this is something that I really want to be sure and have better signal to noise before saying anything about D-wave gaps.
Could antiferromagnet give you similar process? Like you would expect, for example, suppose you have antiferromagnet where, it is like, for example, I'm not trying to invoke the work of Sander, but would it be possible actually to prove like whether you have ferromagnet or antiferromagnet using also shot noise?
With these materials, I think things like ferromagnetism, antiferromagnetism, some mott physics, these things will all have an imprint of the noise. And I'm very excited. Now, Sander doesn't need any help to see if he has magnetism because he has a spin polarized tip. But I would be very interested how that imprints on noise. So if Sander would measure that, I think that would be very interesting.
Okay.
All right. So there's another question by Dario. Dario, please go ahead.
Yes, thanks for the talk. Very nice. You know that there are other quantum materials where you have phenomena of pairing that are quite interesting. And one of those are the excitonic insulators, the holy grail that we never discovered. And then probably, I don't know if it's correct, my naive thinking, probably there you would expect the opposite that you have with your shot noise measurements. So the shot noise, instead of jumping from 1 to 2, probably would jump from 1 to 0 because your exciton pair is charge neutral. I'm wondering if you're thinking to try to make the same type of experiment on materials that are believed to be excitonic insulators.
So we thought about it because somebody once suggested it already. I'm not, it's not something that I'm an expert. We would need something that is STM friendly, which is already somewhat challenging. And then I thought about it, but I'm not yet 100% sure what to be expected, right? Because with all these fractal charges that you'd expect in some ways, it's never quite clear what you have, because in the end, in our case, it's the Andreev reflection that gives you the doubling, right? Because STM, because it's tunneling, it unfortunately, or fortunately, depending on the case, you still tunnel electrons. You don't tunnel any exotic fractional quasi-particles.
Yeah, but sorry to add more on this. You can make a theory of a sort of Andreev reflection for exciton pairs. I mean, you get a physics very similar to the Andreev reflection. The difference is that you're not tunneling Cooper pairs, but you're tunneling charge neutral pairs. See, I mean, naively thinking, the theory developed in the 60s is quite similar to the BCS theory.
But
so sorry, tell me.
I would have expected that, because it's not the charge neutral pairs that you tunnel. But you know way more about this than I do. So I guess that the answer is it would be great to talk more about it.
Yeah, sure. I would be happy about that.
That's.
I will drop you an email later at the end of the talk.
Yeah, that'd be great.
Okay, thanks.
Great. So there's another question by Frick. Frick, please go ahead.
Hi, thanks. I have a question about the fact that you actually measure a charge of 2e, which means that the only tunneling that takes place is through Andreev processes. And as you know, even for tunneling with a normal tip into a regular superconductor like aluminium, there's always a contribution from quasi-particle tunneling, unless you go incredibly close or at very low temperatures. So you would always expect a charge between 1e and 2e. So I'm very surprised that in this strongly disordered superconductor, you measure something that has a charge of 2e, despite having a very large background density of states that I might naively attribute to single electron tunneling. Can you comment on that?
Yeah. So I think that really goes to the heart of what I find interesting about these results. Now, first, a comment about that you made about aluminium. That's true, but I wouldn't call the temperature that you need incredibly low, right? This is lead, and you can see that we nicely see there's no quasi-particle.
Yeah, no, sorry.
Right?
But this is lead on lead, so you have two hard gaps. But if you have a normal tip and lead, then you would expect something between 1 and 2e.
You would just expect a much more smeared out transition, right? Here you would still have 2e, and probably it would start around here, right? So it's just much more smeared out, and you can kind of simulate that with in different ways. You can do this random scattering matrix, or you can do more phenomenological ways. And we try to indicate here a little bit what you would expect. So you would still expect that, you know, if you go to low enough energy, you have 2e. Now, what you said about the gap, you're completely correct. I would have attributed these things to quasi-particle, and in fact, you know, when people measured things in the cuprates or in heavy fermion materials where the gap was semi-filled, people would always attribute it to quasi-particles or to artifacts. And our data is definitely in contradiction with that. Our data indicates that whatever fills the gap is not quasi-particles. We don't really understand, you know, this suggests that this is really kind of a metallic state made out of Cooper pairs, but more details, I think this is to be understood. I agree with you that this is not what I would have expected when we first saw this gap.
Okay, I think what I would propose at this moment is that we can stop the official part. Also, I will stop the recording. We can thank Milan once again. But Milan, if you have a few more minutes time, you can hang around to see if there are some more questions coming. But let's stop the official part here and thank Milan once more. So thanks. It was a really great talk.